Good evening, one and all. Welcome to webinar series conducted by Amity School of Engineering and Technology, Amity University, Haryana. I, Dr. Shubhra Das, Head of Solar Engineering Department, Amity University, Haryana, welcome Dr. Raghavendra Kumar Chaudhary to deliver a lecture on cognitive radio systems. I would like to thank our leadership, Honorable Chancellor Dr. Aseem Chauhan, Honorable Vice Chancellor Professor Dr. P.B. Sharma, Honorable Pro Vice Chancellor Professor Dr. Padmakali Banerjee for their continuous support and inspiration for organizing webinar series in different areas of engineering and technology. Before we start the lecture, I take the honor and privilege to introduce our speaker of the day, Dr. Raghavendra Kumar Chaudhary. Dr. Chaudhary is an academician and a core researcher. He is presently working as an assistant professor at the Department of Electronics Engineering at IIT Dhanbad. He did his PhD from IIT Kanpur in 2014. Dr. Chaudhary has authored more than 110 referred international journal papers. He is currently serving as an associate editor for IET Microwaves, Antennas and Propagation, Microwave and Optical Technology Letters Willy, and IEEE Access. His research interest includes RF and microwave engineering. It includes microwave metamaterials and their application in antenna filter absorber, MIMO antenna array, antenna and SIW antenna and filter, dielectric resonator and its application in antenna and filter, frequency selective surfaces, electromagnetic bandgap, and artificial magnetic conductor structures, finite difference time domain analytical methods. Dr. Chaudhary is a senior member of IEEE and URSI. He is handling many research projects in the capacity of principal investigator, sponsored from various Indian funding agencies like DST, ISRO, DRDO, etc. Dr. Chaudhary and his students have received various awards and recognitions. Mr. Mohammad Amin, a PhD student of Dr. Raghavendra Kumar Chaudhary, has been selected for Young Scientist Award in 2020 at General Assembly and Scientific Symposium of the International Union of Radio Science, Rome, Italy, to be held in August 29 to September 5 in 2020. He will be presenting the paper entitled Compact Dual Polarized Meta-Surface Antenna with Extended Axial Ratio Beam Width for SNC band application. Ms. Ruchita completed her MTech thesis with Dr. Raghavendra in 2018 and has been awarded the INCAP 2019 Best MTech Project Completion Award in the IEEE Indian Conference on Antennas and Propagation held at Ahmedabad, India, December 29. Dr. Chaudhary himself received Young Engineers Award in 2019 of the Institution of Engineers, India in Electronics and Telecommunication Engineering discipline. Dr. Chaudhary has been featured interviewed in IET Electronic Letters UK. There are many more laurels and appreciation received by Dr. Chaudhary at different levels. We are happy to have him here today to share his expertise on a topic which is the need of the hour. As rightly said by Nikola Tesla, when wireless systems, wireless is perfectly applied, the whole earth will be converted into a huge brain. We shall be able to communicate with one another instantly, irrespective of distance. Without taking any more time, I request Dr. Chaudhary to deliver his lecture for the day. Sir?
Okay, thank you so much. Thank you so
sir.
much, Dr. Das, for the nice introduction. So I'll share my slide and then I'll start.
Yes, sir.
Just a minute. Okay, so For today's talk, I have chosen the topic cognitive video system, which is one of our research area, and three students are working with me in this domain. Correct. So before going to the details, actually, I would like to present actually uh, about my institute and the students. So here you can see we have almost all the instruments, all the facility in my lab to conduct the research in the domain of cognitive radio and particularly antennas. So here you can see this is the building actually where the lab is there. So and as Dr. Das already pointed out the research interest, so I'll not read it out. So mainly the compact antennas for the mobile applications, and particularly we are working for the 5G antennas with cognitive radio for solutions actually. And mainly you can see that there are 7 PhD students are working with me currently, and the 4 already graduated. So some of the achievements of our group actually. So we have around published 98 SCI papers, and we have many recognition from international level and national level. And currently 4 PhD students already graduated from my lab and 13 MTech students. And we published many lecture journals like IEEE Transactions, IEEE Letters, and IEEE Landing publications. So let me begin with the outline of the presentation. So I'll start with the integration, and we'll touch to the concept of the cognitive radio, and then jump over the 5G concepts, and we will talk about the technology and concept actually what actually we are doing in the lab. Then finally, we'll try to learn what is MIMO actually and how it will be helping in cognitive radio systems. And then after within the MIMO actually, we'll try to find it out that how to isolation could be enhanced. And finally, I close with my findings actually that we did last year and in the current year. So before actually moving to the presentation, so the first actually, because why student or why anyone supposed to do the research on a particular topic, so there must be some motivations, correct? So the motivations actually like in present scenario, correct, everybody wants a high speed internet, correct? And this high speed internet provides so many things actually to us, like for example this online lecture, one of the applications, correct? We want movies actually, correct? We want online games, and even you can see a picture where uh, Amazon warehouse, the things are automatically moving actually. And in a medical industry we want high speed internet because we want to operate in a real time scenario, correct? And you must heard about the Tesla car, where we need not to be drive. Actually, we need to just enter the destination, and the car will drive you at the destination. So for that, for these things actually, we require a very good internet connectivity as well as high speed data. Okay? So this is one of the things actually, correct? And this motivates us to learn the things and do the things further, right? So nowadays you will be hearing about the term Internet of Things, correct? And the government is also planning in this area, and is providing a lot of funding in this particular domain. So because there are a lot of application of IoTs like smart homes, smart vehicles, healthcare system, smart school, and smart cities, correct? So it requires actually again a very good internet speed and connectivity, correct? Now let us try to understand actually when we are talking about the internet. So first thing is coming is 5G actually, because the term is roaming around. Right now that this thing is roaming around us. We should know about something about the 5G. What are the things special in this 5G? Okay? So the first thing is latency. So here you can see here this latency is less than 1 millisecond. So this is really very important because when, like, let's say if you take an example of medical field, correct? If doctors wants to operate at remote location, correct? So it requires a very good internet and high speed, and it requires low latency so that whatever action he is performing, right, those actions should be appear at the uh, at that point that the operation is going on. Okay? So this is one of the things. Then after we have a device density. So device density here greater than 1 lakh per kilometer square. Okay. And definitely the data rate will be high in a 5G actually. That I'm going to explain actually the 5G forms in my later slides. So let us first see what are the advantages actually over 4G. So here you can see the data rate is around 10 Gbps, correct? Area traffic density is high, it's 10 GB per second per kilometer square. Power consumption is a big issue with the current things. So because of this smart system, actually, we are going to handle the power smartly, and it reduces actually and require 1% as compared to the 4G. Correct. Then after we have the bandwidth issues. Correct. So bandwidth we are getting around 100 megahertz for this thing. And the spectral efficiency is very good, and further the reliability is another thing. This reliability I discussed in the topic of NEMA actually in detail, right? So, so the thing is, like, if you talk about the 5G spectrum, actually, this 5G spectrum mainly from different countries, 3.4 to 3.8 gigahertz. Sorry. So, so mainly this band is actually identified for the 5G system, sub 6 gigahertz, correct? And recently you heard about the news that Jio is also launching. This is at the same band actually, correct? And the further actually, if you see your mobile actually, like, the thing is we are performing many applications, okay, with our handheld devices for iPad, mobiles, laptop. Actually. So if you see, these are the frequency bands actually, right? And if I start from the GPS, so this is the major requirement actually. This is the major requirement, right? Like GPS, without GPS we can't think of this location based services. And further, this UMTS and extended UMTS, these are the frequency bands actually. And further, we are using WLAN services in these bands. Correct? 2G and 3G, we still are using this thing, and most recently is 4G, which is long-term evolution. And these bands are 1.7 to 1.88 gigahertz and 2.3 to 2.4 gigahertz. Correct. Right now, these systems we are using, and these systems are actually using the MIMO system as well as the cognitive radio system as well. And let's talk about this 5G actually, which is we also call it sub 6 gigahertz. Okay, so the band is identified here 500 megahertz to 6 gigahertz. Okay? Another is ISM band, and we know the application of the ISM band. Like one of the very important application in application, which is a microwave movement, correct? 2.45 gigahertz. Right? So this motivates to us that we can do the research in this area, correct? And like if you see this picture, actually this picture motivates and challenging too actually. So you will see the different components over there, and particularly this blue fonts you will see these are the antennas actually, correct? So if you open your antenna, you will see this thing, but I would not say that you open your mobile. This is the right condition, right? So like here you can see this LTE antenna, horizontal polarized, LTE antenna, vertical polarized. Then we have a GPS antenna, then we have Wi-Fi, then we have a Bluetooth application and other antennas. Right? So mainly we have 5 or 6 antennas, correct? And the challenge is that how to place this antenna, the placement study and all the things, correct? How we can manage without interfering these among these antenna elements. So these are the one of the things actually we are looking into it. Here you can see a very critical picture, which is a Samsung Galaxy S mobile. Correct. Here you can see different location where the antennas are placed. Correct. So why I'm actually stressing over the antenna, because this is one of the integral part. Correct? If you can't receive the signal, if you have don't have the proper receive power, it is difficult actually to process the further things. Correct? Now let us understand the self-fold transceiver circuit. Correct? So what is that actually? If you see, this is divided into three parts, correct? And the typical frequency, like this is the frequency for the 2G system. Correct. So here you can see the circuit system. This is a block diagram. Actually, here you can see the power amplifiers are there, the oscillators are there, mixers are there, low pass filter is there, and in between that we have a mixed signal circuit where the DAC and ADC systems are there, and then we have the digital circuitry where we are performing all the operations. So here the picture of the idea of SDR is actually coming, which is a software defined radio. Correct. So this is a typical actually transceiver circuit, you can say. So the thing is, what actually I'm going to touch in this presentation, that how to make this antenna smart actually, so that it could be work, it could be useful for the cognitive radio system, right? So now the thing is, the issue is actually like when we are talking about this thing, this block diagram is okay, correct? One can understand broadly that these are the things, but how we can convey it, how we can do the things, correct? So here you can see there is a lot of circuits are there, correct? I'm not going into detail what these circuits are, correct? But the thing is, those having the electronics background, they can understand there are various capacitor and transistor. These are at the high frequencies, RF frequencies, correct? And some of the matching line blocking capacitor. These are the things. But the thing is, the real challenge is how to do over the micro frequencies, how to do over the high frequencies, correct? So for doing the at high frequencies, correct? If you see the mobile actually, so you will see many number of printed, or I would say actually the right term will be um, the metallic strips running over substrates, correct? These are the printed circuit boards, correct? And particularly the technology we call it a microstrip retaliation, correct? So for that actually, for making the capacitor, inductor, and these all are the things like the things in our lab actually is when the students going into the first year, so the first lab is going in the machine, then after electronics lab, correct? So they students are playing with the capacitor, inductor, and all the things. But these all the capacitor inductor we are using at the low frequency, correct? Not at the high frequency. So for the high frequency, what are the solutions? How we can manage all the things, correct? So this is actually done with the printed circuit board. I'll present some of the details of the printed circuit board in my coming slides, correct? Now, let us understand the sub-6 gigahertz system actually. So it comprises the two things, which is cognitive radio and there is MIMO, correct? These two things are parallelly going on, correct? So the thing is here the lot of hardware is required, correct? Whereas here in the cognitive radio chain or system actually the things are the software based, correct? Okay. So here you can see we have a very intelligent system actually where the spectrum allocation and all the selection and the rejection done by the software smartly, correct? So that because the thing is like the user actually, those user they are availing the services of mobile actually. We can differentiate into two parts, correct? One part is we can say a primary user, another is secondary user, correct? So the thing is like primary means those who purchase the license actually, correct? And the secondary users, like the thing is those the thing is not we are not going to give the priorities, correct? So the thing is whenever we find the spectrum hole or we are saying the white space, correct? So how we can smartly use this smart space so that others user would be also benefited, like like if the channel is limited, correct? So others can also be utilized in this way. The spectrum efficiency could be improved, correct? So this is the idea of the cognitive radio system, correct? On the other hand, this MIMO actually nowadays very famous, correct? And we need to understand these things in a detail as well, and I'll try to explain some of the parts how we are doing a lab, correct? Because this is my research area, and mainly we are interacting with the hardware and making the hardware systems, correct? So this MIMO is referred as multiple input, multiple output, correct? So this picture actually I taken from a company actually. That company is making this array kind of antennas. This is a MIMO antenna actually. So here you can see this. These are the patches actually, circular patches. These are nothing but a metallic patches, right? Arranged in a such a fashion so that we can get a proper far field property of the antenna, correct? Now let us understand the cognitive radio actually, correct? So there are some definitions, right? And we need to understand what they are. So this is actually done by the FCC, correct? And according to FCC, what they this is this a radio that can change its transmitter parameter based on interaction with environment in which it operates. Right? It means it's sufficient having the intelligence so that it can accommodate all the things. Right? So these devices can dynamically modify their operation parameters such as frequency, modulation, scheme, and transmit power to make best use of the available spectrum and other resources. Correct? Now coming over the radio, actually this term we are daily means listening this term in our daily life. That radio actually and this makes sense in the transistor earlier time. So here the radio actually defined as the technology for wirelessly transmitting or receiving EM radiation to facilitate transfer of the information. Correct? So basically a system which can receive and transmit the things. Right? So mainly we have all under system which falls in this category. Correct? And then after things term is coming software defined radio. Correct? And this is very important. Correct? So here, what is SDR actually? SDR is a radio in which the properties of carrier frequencies, signal bandwidth, modulation, and network access are defined by the software. Correct? The thing is, these all the operations we are doing by the software actually. Correct? Now, let us understand the cognitive radio cycle. Correct? So this cognitive radio cycle, if you can see here this thing. So there are four major blocks are there. One is observe. What we are actually doing in a daily life, the same thing actually the cognitive radio cycle. One is observe, another is decide, then act, then we learn. Means the first thing we have to observe the spectrum. Correct? Is what the spectrum we are using. Correct? And where the white space are there. Then we have to decide. Correct? If you are getting the opportunity that the white space are there, correct? So that secondary user can be use these things. So this would be decide actually, and then finally the system will be acting that will accommodate the things that okay this particular space is there. So the secondary user can be worked at that particular band. Okay, and then whole process going to be learned. Correct. So you can say this AI and all the things will be playing a big role actually in this. Correct. So there is one of the area where AI could be implemented, and even the things are already going on. Correct. Now let us understand the software defined radio SDR. Correct. So if we take the hardware, correct. So it start from the antenna and RF tuner, then ADC. Then we have the digital dump converter, this unit, correct? And we have the digital processing unit, correct? So this is actually my part, you can say, correct? Where I am working. So this antenna, RF tuner, and these things, a little bit of this is the ADC part, correct? And this part is handled through the software after the converting to analog to digital, correct? And finally, it is processed digital processing and all the things we are this happening here. Now, this is a receiving chain actually, and same as for the transmitting chain, we have a DSP, then digital up converter we have, which comprises here the filter, digital mixer, and the oscillator. Then we have the down D to A converter. We have the RF disease converter and power amplifier antenna. Just reverse of the above. Right? So this is one of the things. Now here this SDR actually. The thing is basically this part is hardware, and up from here actually we have the software part where we can intelligently control all the things. Correct? Now let us try to understand what is cognitive radio system. Correct? So as we discussed that cognitive engine, and we have seen that how the cognitive cycle is working. Correct? So this is observe, decide, act, and learn. Okay. So this is we call it the cognitive engine. Now the thing is when we integrate with the SDR platform. Correct? So this is what we have. This is a complete SDR. Correct? It comprises here what a transmitting channel as well as the receiving channel. Correct? So when these two systems are combined, so we are saying it's the cognitive radio system. Correct? Now the thing is like so many parts of so many components. The things they are already commercially available and designed like the SDR part. Okay, SDR part is well available in the market, and we can utilize the thing straight away. Correct? Now the thing is the problem with this hardware particularly with this antenna actually. So what happens actually for the antenna part, like it requires the different operations. Okay? To run this cognitive radio system. Correct? So what it requires actually, it requires the wideband sensing, the narrowband sensing, and the band not sensing. These three operations we require. Now the thing is earlier, if you check the literature survey and the previous work, correct, what you will find they are doing they are trying to do from the different elements actually, correct, and somewhat it makes the system bulky, correct. So what we did actually, we tried to combine these things, correct. This is one of the unique things which we done in the lab, correct, and we are telling this is one of the unique things, and I'm going to explain that how we combine all those things and what are the components we clubbed actually, correct. So let us understand once again the cognitive radio devices, correct. So the thing is, first we need to differentiate how the secondary user can access the spectrum of the primary users. Correct? So we can understand these things from these two operations. Like one is the spectrum interweave, correct? Another is spectrum underweave. So what is happening actually? You can see the different color I have given here. So PU stand for the primary user, whereas SU stand for the secondary user. Correct? So whenever we have the white space, we can see the secondary user start working. Correct? So this is comes under to the spectrum overlay or spectrum underlay. Correct? Now on the other hand, the other thing or other way to see these things or provide the spectrum the efficiency, we improve the efficiency. We have the spectrum underlay, correct? Where you can see I marked a line, actually a dotted line. You can see, correct? So whenever the primary user, correct, means below this line actually secondary user can work easily, correct? There are no restrictions. But as soon as the primary user, secondary user crosses this line, correct? So the secondary user stop working in this area, correct? And the primary user going to dominate. Now the thing is, these operations require an inherent system, which is actually cognitive radio. Okay? Now the thing is, like how we will do this thing. Like here, like try to understand what the operation actually we require. Okay, to settle down the things here. One is when we have the white spaces, correct? How to build the white space, correct? It requires a wideband sensing, correct? And it requires a tunable system which can sense the system. Okay, so and here on the other hand, if you see here, we have a interference level actually. Above that, the primary user will block. This is the rule of the game, correct? And below that, the secondary user will block. But this interference, correct? If the secondary user crosses this interface level, then how to stop this secondary user? We need to understand the mechanism. So for that, we require the proper bandwidth system, correct? Means ultimately we require the proper bandwidth filter actually, correct? So that the operation could be performed. Okay. Now, so this is the overall thing, correct? This is a cognitive radio system architecture. So I clubbed all the things. This photograph is actually taken from this magazine actually, correct? So this is in a compact way we done it, correct? So here you can see this is the SDR system, and this is a physical layer, correct? And this is the MAC layer. And here you can see that this is the one important block is there, that core sensing and the fine sensing, correct? So that core sensing and fine sensing actually is going to work for these two things, correct? Means we need to find the tunable system so that it can better detect the white frequencies, and the fine sensing means that it can detect the proper interference level, correct? So here we have the options here so that we can do these operations, correct? But the thing is, we require a tunable filter and all these things. So what we are actually doing in a lab, correct? We are making the integrated system, correct? So that the instruction could be directly given to the antennas, and these operations could be performed easily, correct? However, this could be also performed, but the thing is, we are trying to reduce the hardware complexity, correct? This is one of the aim of our research, correct? Now the thing is, like we got some sense about the 5G systems, correct? And particularly what are the bands actually, correct? So let us talk about some technologies actually. So one thing is where I want to summarize this thing, that cognitive radio and the cognitive system and devices, which requires the intelligent systems, correct? Which can detect the white space, which can detect the minimum power level, where the secondary user, they can give the opportunity to secondary user, they can also utilize the band. And in this way, we can improve the spectrum efficiency. Okay? So the thing is, if you talk about the 5G actually, so there are mainly two things are coming. Okay, one thing is sub-6 gigahertz, another is millimeter waves. Correct? So what is the technology involved? Like if you are talking about the sub-6 gigahertz, which you guys are going to use in couple of months, correct? This is MIMO, cognitive radio, massive MIMO, and its advantage are this can travel longer distance, correct? Penetrate through the obstacles, and there is a cost factor. And if you talk about the millimeter wave system, so it consists of MIMO, phase array, beamforming, and SIW. SIW stands for substrate integrated waveguide. So this is capable of handling the high powers, correct? Now, so what are the advantages here? Here the advantages are this is a very high data rates, correct? Because the frequency band at the millimeter wave, correct, is 28 gigahertz or 32 gigahertz at that range, correct? So we can expect the more bandwidth and the high data rate. Whereas this is a 6 gigahertz, we are talking below 3.2 to 4.2 gigahertz, correct? So what conventionally we are moving out of mobile almost at the same frequency, because this is 2 or 2.5 gigahertz, and now we are going to shift to 3.2 gigahertz, correct? Now the thing is actually this part actually, this you can see, this is the real 5G actually, where we are going to get a low latency system, high data rate, and all the flexibilities, right? Now the problem is that, like if you go with a millimeter wave, the problem is the loss actually. The higher frequencies can't penetrate the obstacle, correct? And it stops the long distance communication. We are going to restrict the communication within a certain region or certain space, correct? This is the one of the things. Otherwise, we have to do the with the repeaters and all. And this is one of the cost factors that companies are not moving towards the millimeter wave. This is still a lab-based item, correct? So basically, the research is going on. Still, we are also doing things in this domain, and hopefully I'll do this thing and will present the results some of the video. So our focus is that sub-6 gigahertz, correct? Let me clear you that our focus is sub-6 gigahertz systems, correct? Where we are doing these all sort of things, correct? Now the thing is, Now I'm going to start some of the real hardware part actually, what actually we're doing in a lab, correct? So, okay, so I have half an hour. So, so what are the antenna requirements, correct, for the incorporating the cognitive radio technologies, correct? So as I told you, these two things, one is the interview, another is the underview, correct? And this is a cognitive radio front end. Now, the thing is, the components are required to do such these operations, what I discussed in previous slides, correct? These are actually wideband sensing. These are the common in both the schemes, correct? Other is the narrowband sensing, correct? Other is the narrowband sensing. So now the three we can see here the three operations are there. One is the wideband, narrowband, and the band not sensing. Correct. Now the thing is like how we will incorporate all the things in the antenna. Like if I say about the antenna actually, this is a transmitting and receiving device, correct? And if we fix the band is going to radiate within the band and all the things. But these features, how we can accommodate it, right? This is one of the challenges I would say that within the small space, how we can accommodate these things because ultimately I'm going to reduce the complexity of the hardware, right? So, up to here we have seen the cognitive radio, correct? Now the thing is how we will see here we will see that what is MIMO actually and its integration, correct? So first let us make some background of the MIMO actually, and let us try to understand that what is MIMO and why this MIMO is important, correct? And why this MIMO is actually going to enhance the data rate, reliability, and all sort of things, correct? I'm going to explain. Then after, what we do, I'll merge this, correct? Now, so before moving on this part, actually, I would clear some of the facts that what technology and the concept we are using, correct? So the technology we are using, which is a microchip, correct? What is a microchip? We already have the idea about the PCB, printed circuit boards, correct? This is the same kind of things where the upper and the bottom part is made of copper, and in between the electrical sandwich, correct? Now the upper part we are making actually capacitor and inductor and all the things, right? And this is at the micro frequency one of the challenging tasks I would say, correct? This is not a cup of tea actually, correct? Because the thing is realization of the capacitor and inductor at such a high frequency and managing all the things requires somewhat the background as well, correct? So we have these things, correct? I'll try to explain what we did actually, correct? So here you can see some of the photographs, correct? So this is the application of the printed circuit board, correct? Where these black lines, this things you can see this is the metallic part, and we try to arrange this such a way that it could be actual ground or the radiator or the filtering elements, correct? So these are the electric and magnetic fields. I'm not going into detail what is that actually, correct? We'll try to connect it how we can connect with the system, right? So the thing is, before try to understand this thing, conventional microchip actually we need to understand the conventional transmission lines. So we already aware these two-wire system, correct? Coaxial wires, correct? All the things we have seen in our home actually, correct? And frequently we are using as well, correct? So the thing is, why I'm saying this is not cup of the tea actually, like the students, those who are UG students, so they must interact with this register, capacitor, inductor, and all those items, correct? Now the thing is, these are frequently available in our lab. We can utilize, we can use, put in on a breadboard, and we can make circuit, and the task is completed, correct? But the thing is, when we are talking about the RF, correct? So RF actually will provide the extra dimension, and the thing that this is the distributed theory going to be applied. Means the thing is, we cannot say a particular thing will be acting as a capacitor or the inductor, correct? Because this comprises the short of the electromagnetics, correct? So like I'll give you a very small example what you studied in class 8, correct? So if you have the small segment of the wire, correct? So what will happen? This small segment of the wire, if it carries a current, correct, it having the magnetic field around this, correct? So this magnetic field, because due to the Faraday's law, the magnetic field could not be alone actually. So it having the magnetic field too. oh sorry, electric fields too. Okay. So the thing is, due to the enough flux around this wire, okay, this could be acted as an inductor. But at the same time, there are some state capacitance too. Correct. So the thing is, you can see here, I draw a wire actually, a coil actually, and here you can see the 3 or 4 terms. Right? What is this wire itself providing the inductor, and the gap between these two provide capacitance, and the ohmic loss will provide you the resistance. So this is really very complicated if you see, right? That a coil shape will provide you 3 things, which is a resistor, capacitor, and inductor. Right? So this is not easy to handle. Correct? That is why I'm saying. Correct? So this is one circuit model of the conventional transmission line. Correct? So as I told you, the electrical magnetic. So here we can see the inductor and capacitor is forming, and finally you can see here, this is one of the transmission line. Let's say a 2-wire transmission line. So the equivalent circuit could be understood like this. Correct? So here we have an inductor, we have a capacitor, and all sorts of things. This is a model. We try to make a model so that we can do theoretically these things. Correct? Now, these are some of the planar transmission lines. Correct? So this is one of the very well-known structure, which is microstrip. Correct? Frequently, we are using to making our circuits, and these are some other circuits as well. And particularly the second one, we are using coplanar waveguide CPW actually. So here, what is happening actually? On the same ground plane, we have the ground. On the same plane, we have the ground plane. On the other hand, in the microstrip, we have the ground plane at the beginning. Correct? Now, if you talk about some of the microstrip is not a new thing actually. Correct? It invented long back, and particularly here, the mode is not TEM. This is a quasi TEM. Correct? These are the field configuration. Correct? Correct, and these are the sum of sort of the equations, correct, what we use to calculate the effective permittivity, phase velocity, beta, and z0, and all those things. Because the thing is, we need to properly calculate, correct, what is the impedance. So, like, impedance is one of the very important things. Like, means in your home, actually, we are using the DDA services, Tata Sky, and all the things. Please check, correct, at the back side of those things, correct. So the cable which is coming from your antenna is connected to that setup box, right? So you will see that impedance written over the box, which is 75 ohm, correct, and sometimes it is 50 ohms, correct. So actually the thing is, we need to find a system which can support these impedances, correct. So these are some sort of formulas actually. These are the available. These are textbook formulas. I'm not going to explain this thing, but you means those who want to start the things, they're supposed to start with these formulas so that they can make the initial guess actually to design the system. Correct. Now let us try to understand quickly what is MIMO actually. Correct. So the thing is, like, this picture actually is really very good. I took from this magazine actually, tutorial. Correct. This is from published in 2016. So you can see this is two antennas are there, and we are the users actually sitting in the car. We have a mobile, these things. Like in between, there's a building actually. So like when this antenna is transmitting, so the signal is going to stop by this building, and maybe trees and some other physical things are also there, right, in a real-time scenario. Correct. So the thing is, like due to this multi-path propagation and reflected signal, sometimes we are losing the signal. Correct. And remember, when the time of the GPRS, correct, the 2G system, correct, or the 3G, it is difficult to maintain the proper connectivity and all the things, because that time this MIMO and all the things was in the research actually, and in 4G actually we got this MIMO actually, and we have very good connectivity, and this is all the applications we are using nowadays. Correct? So the first thing is, this is diversity scheme. Correct? So particularly diversity scheme used by the two domains. One is the communication engineer, another is the RF engineer. I'm the RF engineer, correct? So I will be talking about the antenna diversity. Correct? So what is this? This antenna diversity means like frequency and time diversity. Like you can play with the time and the frequency, these things in different modulation scheme and all. Correct? But I'm not going to talking about these things. Right? I'm going to play with the antenna diversity. So one is the spatial diversity, like CMO, MISO, BMO means CMO stand for single input material output. We also stand for the multiple input, single output, and MIMO multiple input, multiple output. Correct. And the polarization diversity is horizontal and vertical actually. Correct. So like, this is one of the real-time example actually. I try to catch these things. One of the magazine actually. Right. This is the article you can also read. So here you can see this person actually, cameraman is shooting actually, trying to capture the video actually of some event things. And the thing is, if you carefully see this thing, so you will find the two antennas actually over there, correct? And these two antennas are placed at 45 degrees, correct? It provides actually good polarization diversity, correct? So this is one of the way actually we can place, correct, these things at 45 degree apart or 90 degree apart, correct? But this is not a solution many times actually, because the thing is, we are habitual in the mobile and we want to put everything in our pocket, correct? We want to put them in the pocket, and if these kind of antennas are there, definitely we cannot put in the pocket, correct? Now, so these are the various schemes, correct? And the thing is, the things are started from CISO and we reaches to NIM, correct? And if you see, we have the first system, which is single input, single output. We have no diversity, right? Whereas CMO, we have the diversity at the receiving end because there are two antennas, correct? I'm going to tell you what is this, correct? And then after we have the transmit this thing, diversity, because we have two antennas. Now we have N antennas here and N antennas are here. So we have the transmit and receive diversity. Correct? Why this is important? Let us try to understand. Correct? From this things. Correct? So we have, let us take a CMO system. Correct? Single input, multiple output system. Correct? And let's say we have one antenna we place at here, and these are, let's say, user. Correct? Now this antenna is transmitting. Correct? Is transmitting and receiving this both three parallelly going to happen. Correct? So let's say the things are transmitted and these are the obstacles, and let's say from multi-path detection and filling and all the things, let's say the path number one actually the signal is going to lose, correct? Loses actually, correct? So what will happen? This is the channel actually. So H11 will be 0, correct? Now the thing is, let's say we are in a fluffy, correct? And we have the MIMO system, correct? So our second antenna is going to receive the things, correct? And in this way, H21 will not going to be 0, correct? So here they are going to receive the signal. So the thing is, this provides the diversity, correct? And in this way, we can improve the reliability too, correct? Now these are the channel capacity formulas, textbook item. I'm not going to detail, correct? So one can find these things, correct? The channel capacity, the channel and all the things are known, correct? Now here I'm trying to explain the things like how the spatial diversity and spatial multiplexing is work. Like if you see here the same data, if I'm going to feed in 3 antennas, so definitely the same signal is going to propagate from 3 antennas. So it will improve the reliability of the system, right? But at the cost of the data speed. But the thing is, let's say if I'm planning to make one bit particular at a particular antenna, so in this way I can improve the what data rate, correct? So these are the two things actually in a MIMO, correct? So this is one of the feature actually I tried actually to make here to explain, like this is what we have one mesh actually or channel, I would say. This is 0 to 100 megahertz and divided in 10 channels, correct? So let's say one bit is taking things 1 second, like that, correct? And if we use QPSK modulation, correct, where the 2 bits represent one symbol, correct? So if you try to find it out the speed, so it will provide you 20 bits per 1 microsecond, correct? Now the thing is, we can improve this data rate by improving by taking the different modulation scheme, but it will deteriorate actually the bit rate, which is bit above 1. So what is the alternative way? We can use a MIMO, correct, which can improve the data rate as well as the diversity too, correct? So here we accommodate that 2 plus 2 MIMO. Correct. Now the two symbols are going to handle by this single unit, and in this way data rate is going to be double, correct? So this is one thing, correct? So in this way the data rate could be double, correct? These are the advantages. I already explained the thing, so I'm not going to read all those things, correct? Now these are the parameters we are realizing this MIMO. that these are the 6 parameters, right? 6 parameters here. We are going to judge actually the minimum performance of the system. One is the isolation, another is envelope correlation coefficient, then the gain diversity, arc, total active reflection coefficient, channel capacity, and the mean effective gain. Isolation is one of the important parameters, correct? And the thing is, when we are trying to perform the MIMO actually on the same substrate, since number of antennas are very crowded and crowded systems are there, so really it is difficult to maintain this thing. Like you heard about the electromagnetic interference. Like, uh, one of the real example you may understand, like that, when you are talking, like, if you are using the landline this things mobile this telephones actually via telephone, and if you are simultaneously you are using mobile phone, you are getting some disturbance actually, right? So this is your electromagnetic interference. Now the same kind of phenomena is happening when we are using the number of elements over the same substrate. So the antennas elements are talking to each other, correct? So when the antennas are talking how to improve these things, so for that actually we require solution of mechanism so that we can improve the isolations, correct? Then after envelope correlation coefficient, this is one of the powerful phenomena when when the antenna is radiating and going in a space actually, correct? So there must be correlation between the radiating fields, correct? And we are supposed to reduce it, correct? And for that we have certain things, correct? And then after channel capacity, I'm not doing all the details actually, but these are the parameters we are going to discuss. So simply, I'm going to explain the isolation part here, correct? Which is I'm thinking is important actually to make the system actually, correct? So the like isolation, what we are doing in a lab to enhance this isolation with these things. So mainly these 5 techniques are available in the literature, correct? So among these 5 actually, we are using the reflector base, filter base, and emphasis base, correct? So these 3 techniques we are using. I'm going to explain the filter based isolation technique, and further what we made actually means what 5G system, what 5G communication system we made, I'm going to explain with this reflector based system, right? So this is one of the published paper actually with my students, IT micro antenna published some of the results actually, correct? So this is MIMO antenna. I'm not saying this is the 5G antenna or this is saying this is just a MIMO antenna, correct? I want to explain that thing, that whatever I told about the MIMO, I'll try to explain these things with the help of the hardware what we develop in the lab, correct? So this is the picture actually, correct? And what is our claim actually? So what we are claiming that this is the first thing, first system where we incorporated the isolation, correct? As well as the miniaturization. How did the miniaturization? We tried to accommodate 2 frequencies, correct? The 2 frequencies are what? That the 2.5 gigahertz and the 5.4 gigahertz. So we accommodate the 2 things on the same substrate. So the thing is, these are some simulation results, correct? And you will see here, these are the 4 antennas are there, right? We placed over these things, and this is at working at 2.45 gigahertz, right? And similarly, the second system, when we remove this middle line part, correct? So it is now operating over 5.4 around 5.4 gigahertz, right? Now, if you see these pictures actually, so you will see when we put in the source at antenna number 1, so these two sectors are also means having some electromagnetic field over there, right? And the thing is that is actually you don't want, correct? You don't want this kind of thing, because when we are exciting this element is supposed to be alone working. It's not like that these systems are working, correct? So for that, what we did, we make a coupling network, decoupling network, and this decoupling network we inserted over here, and we improve the isolation. Now here you can see these things, like these things, like when you are providing the input at this antenna system here, correct? So here when the system is without the decoupling network, so you can see the red color, which indicate that there are electromagnetic field over there, correct? So the thing is, it means that antennas are talking to each other. Now, once you accommodate the decoupling network, correct, you can see that you can see their antennas are not talking. So this is one thing actually, correct? And at the same time, at the system working at 5.8 to 5.8 gigahertz, correct? This is true for that, correct? After that, what we did, we incorporated some pin diodes, correct? And by using the properties of pin diodes, we can on or off the system, correct? And we can accommodate the two frequencies easily, correct? So these are some measurement results, and we validated these things, correct? So these are the design methodology, correct? I'm not going to detail this thing. I'll tell you this thing when 5G antenna I discuss. So the thing is now we have the enough data. But we have a cognitive radio system, and we have the MIMO system as well as the placement of the antennas and all. Now we are going to integrate this system, correct? So now if you take the literature actually, correct, with 2020 as well, correct, you will find that the system developed for the different thing like overlay or underlay system. It is not working for both the system. Correct? Still, but the thing is, last year, which is in 2019, we tried to develop a system which can accommodate two things, two schemes, overlay and underlay. Correct? And this could be possible within the single area. Correct? And here I put it these pictures. These pictures are I have taken some of the journals of different authors, different research groups. They trained actually the antennas or the RF end, right? What I talked about in the cognitive radio system. Right? So you can see here we have the wideband sensing antenna, reconfigured filter and biasing. What we did actually, we accommodated all the things in the same same area, correct? So this is one of our work actually recently published in Metabolic Transition on Antenna and Propagation, one of the major journal in the field of antennas. And this is the photograph of the cognitive radio system actually, correct, what we developed, correct, in our lab. So what are the design considerations here? That MIMO, what I talked about actually, and the mid-band 5G frequencies, 2.5 to 4.4, and for the 5G applications actually, correct, with cognitive radios, we require at least 4x4 system, correct, and isolation we try to maintain less than 15 degrees, correct, with the help of the reflector. And finally, the cognitive radio cycle, correct, we try to make here actually so that it can intelligently sense the spectrum and the sharing techniques actually, correct. Means particularly this is going to work for interleave and underlay system, correct. This is our claim is that we are the first actually where we develop these things actually, correct. Now the thing is, this is the single antenna element, correct, and we placed in this arrangement where the 4 antenna elements are placed, correct. Now if you see these curves actually, these curves tells about the input reflection coefficient, and here this provides below 10 dB, this is 2.5 to 5.5 dB, correct. Now once you placed in this fashion, correct, so the thing is other parameter also start coming. What these parameters? This is S21, S31, S4, and these parameters told about you. This is the isolation part, or that how the antennas are talking to each other. Right? You can say in a language actually. So here the thing is, if you see these curves, blue, green, and this red curve, this is coming around -10 dB and all the thing. This is not acceptable actually. So what we need to do, we need to provide a better isolation mechanism, correct? And for that actually we provided a reflector-based isolation scheme. Now the thing is, if you see this curve, correct, you will find that all this S21, S31, and all this is roaming around -20 dB, and this is what actually we want to achieve, correct? Now this further validation could be achieved from this picture actually, that these two antenna particularly I have taken. So when there is no decoupling scheme or based isolation mechanism, then these two antennas are talking to you. You can see some fields are over here, some fields are over here. And this we are fielding actually at here. That is why fields are here. Otherwise, we are getting some here. Fields are here also. And we don't want these things. Now, what we did, we arranged a reflector-based thing. This is purely calculated, means all the capacity, inductance, and all the things we calculated, correct? And based on that, we developed our reflector at this frequency. Now you can see there's a no interaction between two elements, and that is we want actually, correct? And we succeed. Finally, this isolation we improved, correct? Now, after that, we will just discuss about that how to manage the overlay underlay kind of situation, these things actually scheme. So for that actually we require a multi-functional filter, correct? What is that actually? Multi-functional filter, correct? Which can do all sort of operations. All sort of operations means it can be wideband sensing, it can be tunable, it can be band reject, all sort of operations it can be do. Correct. So this is one of the very these things common structure actually in RF engineering called distributed resonator we use to make this multifunctional filter. Correct. So here you can see we put in a vector diode at this place and we got a very nice response here, which is band reject filter. Correct. This is a band pass filter actually, and this is provide the tunability when we are making it provide the proper biasing. Correct. Means like your SDR can do this performance of this thing. It can vary the different voltages and this could be sensed actually. So physically we can sense. It is not like that after D to A big converter we are doing the things. Before that we can make the things, and this could be reduce the system complexity actually. Okay. Now after that we use the pin diode and we make it suitable for the all pass filter. So here you can see this is the red dotted curve actually, and this shows actually the all pass response, correct? And finally, what we did actually, we placed some more pin diodes and all the things, and finally we can see here this is the transmission response, and here by changing the different voltages, this can be smoothly vary in the band, correct? This is the band reject. Now we accommodated all these things, correct? And what we did actually, this is some kind of matching work at the RF frequencies we perform, and we try to accommodate this multi-purpose filter at the feed line. Correct? This is one of the challenging tasks because same signal is going to be fed to antenna, and this is passes through this multi-purpose filter. Correct? And these are the biasing lines which you can understand like that. And here, this biasing line, the use of biasing line could be utilized as like you can change the different voltages and you can perform it for the different schemes. Correct? So these are some of the response, actually final response. So here you can see we have a wideband response, correct? Which is first thing, correct? First requirement. The second was we have required the tunable thing. Now here you can say this is a tunable band pass response. The third item is that the band reject response. Now here you can see this is the band reject response. Now the three things we accommodated in a same hardware system. Correct? This is one of the magic actually we performed in the lab. Correct? Now after that we fabricated the structure. Correct? And if you see this is a pretty big actually. Correct? Now right now the thing is we are working that how to initialize it. We succeed actually, and I'll show you some of the structure we try to accommodate in a small area actually as well. Correct? And this is the complete circuit diagram. I'm not going to detail things, correct? And this is the major result. We tested these things, correct, in a lab. We found this is suitable and could be utilized, correct? And here you can see the simulation measurements perfectly matched actually. Okay, and these are the different NEMO parameters like ECC, efficiency, S1, and all these things, right? And this is the radiation pattern of these things, means how the antenna is radiating in a particular direction, right? So we can see a complete package we have provided, hardware package we have provided, which can accommodate the interweave and the underlay things in a same system, correct? So I would like to read it out. This is things, correct? Is the outcome of the NEMO CR system, correct? It is a tunable range of the interweave CR communicating antenna, correct? 850 megahertz, then 1150 megahertz. Then we have the isolation 15 dB. Then we have ECC better than 0.5, and we have the dark 2.5 to 4.2 and distance, correct? And about the reduction, we try to manage the same thing same performance within the small size. And we published this thing IEEE antenna and wireless propagation letter, and the size is here reduced 48 points. This is a different structure with the same applications actually, correct? So this is all about the things. These are the references actually I used, correct? And these are the students actually who contributed actually this work. This is T. Srinath Reddy is working with me currently as a PhD student, and he's a pass out student, MD pass out student. So thank you for all. And if you have a question, I'm open for question answers.
Thank you, Dr. Raghavendra, sir. We are very delighted to have your lecture today. It was really amazing. It was really very informative, and I hope all the students and faculty members have understood and learned something from you. It was really very wonderful task. So I have a question in my chat box. Would you like to ask from Anil Kumar Mishra, Amity University, Haryana? He is asking what technological effort needed to convert 4G to 5G. Am I
like the thing is, like the thing is, like so many things, so many aspects, and so many dimensions we supposed to work actually. Correct. What I'm doing in a lab, correct. That the thing is, we are making integration between the cognitive radio and the MIMO actually, correct. So that like I have shown earlier, the hardware particularly they have the tunable filter and all sort of things, and after A to D converter, the things are happening. Now we are providing the extra freedom to the these things user, so that they can, or they can manage actually from the hardware itself, so that hardware complexity can be reduced, correct. And this is one of the major challenge actually, because the thing is like this intelligent spectrum sharing is one of the things by which actually the things, or the reliability and the data rate could be improved actually. So hardware side, I would say that the challenge is like how to integrate. First thing is like if you're working in a sub 6 gigahertz, how to integrate this MIMO, cognitive radio, and all sort of things, and like 5G in millimeter waves, correct. We supposed to come across with a beamforming and like infrastructure at the millimeter wave we supposed to handle, correct. So these are the challenges actually we need to accommodate.
Hopefully, the question has been resolved, what the participant has asked, I hope. So, Dr. Shubhra ma'am, do you have any question in your chat box?
Yeah. Hello, sir. It was such a wonderful talk. There are a few questions that has come from Professor Sikka. What is the scope of AI in cognitive radio systems? And there's another, I put both the questions together. And another is, will fiber deployment patterns change when 5G is developed? This is from Shweta Sinha, Dr. Shweta Sinha.
There are two questions actually.
Yeah. What is the scope of AI in cognitive radio systems?
AI, yeah, correct. So actually, like I told about the cognitive cycle, correct. So the thing is like the three blocks, four blocks actually, and one block was the learning scheme, correct. So the thing is like how we can find out the white space, correct. Means particularly the empty space where the secondary user can work, correct. So these things are going to do means we have to provide the instruction, and the wideband antenna will means the wideband antenna and all the things gradually do their work and try to find it out the things. But the thing is like these things like if you try to find it out or make the data big data actually, you will find some similar opportunity repeatedly happening. And this could be if AI is there, right? This could be learned, and this is learning scheme can provide a better actually understanding to the system, so that smartly it can sense this white space and could be utilize the thing. So this is the thing actually, but I'm not actually very much familiar with AI and all the things, If the person wants to collaborate with me, correct, in this team, I'm ready to do the things, correct, because hardware part I can do, and the AI part could be done by the these things. Okay. Yeah.
I think, Professor, you are satisfied with the answer. Now I would like to ask, request Dr. Khushbu to propose the vote of thanks. Hello, am I
Okay,
audible?
ma'am. Yes, there was another question. If you allow me, can I ask
Sure, sure.
from the
Yeah,
speaker?
please, please, please.
So the question is from Dr. Shweta Sinha. She is asking, will fiber deployment patterns change when 5G is deployed?
Yeah, I don't have this things idea about the fiber and all actually, correct. So I would not take these things in this question actually, because the thing is like the fiber and all this is other domain I would say, correct. I'm not actually I would say aware actually with those things, correct. I'm particularly working for the transceiver systems, correct, and this is all about, correct, these things.
Thank you so much, sir, for your answer. I know you are the master of antenna and you do not want to leave this research area, what I know about you. So I am Dr. Khushbu Tripathi from Department of Computer Science and Engineering, Amity University, Haryana, Gurgaon. I hope you have all enjoyed the lecture asset organized by today. And it is my honor and privilege now to give a vote of thanks to all those who have made this webinar a success. So I express my sincere gratitude to Professor Dr. Raghavendra Kumar Chaudhary sir for sparing his valuable time to be with us
Thank you,
this
thank you.
evening and sharing his rich experience in the field of antenna, microwave, MIMO, and etc. Specifically the word which I highlighted, that is SDR. So it's really very insightful, the software defined radio which you have discussed in your lecture. I'm very thankful to you, sir, for sharing your rich experience in the terms of research and area with the
Thank you.
faculty members and the students. I would like to express my gratitude to Professor Dr. P.B. Sharma, Honorable Vice Chancellor, Amity University, Haryana, for his continuous support and guidance in the research and innovation at Amity University, Haryana. He has been always a driving force for all of us, to the students and the faculty members. Now, next, I would like to thank Honorable Pro Vice Chancellor Ma'am, Professor Padmakali Banerjee Ma'am, for her inspiration and motivation in the pandemic situation to keep faculty and students motivated. Her leadership has taught us how to turn everything into an opportunity. I must thank our director, sir, Dr. S.N. Sridhara, from the ESSEC and AIIT. Because of him only, this webinar was successful. So for his tireless effort and the best of the word from the academia and industry he has given to us, and in the Amity of University of Haryana, we are really thankful to the director S.N. Sridhara sir. Thank you, sir, for your support and making this webinar a success. I must not forget to thank all the head of the departments, faculty members, and PhD scholars who had been a wonderful audience for the event and have made it more interesting by participating and actively during the session. I would like to thank my wonderful audience, the participants who have joined and listened the lecture by the Dr. Raghavendra sir. I must thank to the IT team who had been a wonderful support system for this webinar. So thank you for the whole IT technical support system. Finally, I would like to thank our Honorable Chancellor Sir, Professor Dr. Asim Chauhan Sir, for his support and inspiration to all of us here at Amity University, Haryana, Gurgaon. I would like to thank you, sir, and I would like to thank once again who has joined today and make the webinar successful. Thank you.